Dilek. In the previous classes, we had discussed about few types of function and its derivative. Okay, so today I'm going to introduce a new function, or else I can say that I will be introducing a new way in which we can write a function. Okay, so that is function in parametric form. Okay, so this is another way of writing a function. Function in parametric form. And we shall see when a function is in the parametric form, then how we will be differentiating such functions. Okay, so this is the topic which I'm going to cover today. Okay, now you know how a function is written earlier, either that was in explicit form or in implicit form. So these are the two ways of writing a function till now. So in explicit function, what we do is we express y in complete terms of x, right? So when you differentiate that, so directly you can write dy by dx, that is the rate of change of y with respect to x. Okay, or the function was expressed in implicit form, that is, in such case, in implicit function, what do we have? All the x and y terms are mixed together, and then together we differentiate it, and at the end we write dy by dx is equals to with that express, right? Now the third, every time it is not that the function will be expressed either in explicit or implicit. Okay, so we have a third way of writing a function, that is a function in parametric form. Okay, now in this case what we do is we introduce a third variable t. Okay, so right now what we have is our function. We always express our function in terms of x and we represent that with y. So we are dealing with only two variables, x and y. Okay, now what we are going to do is we are going to express x and y in terms of a third variable. Okay, earlier we have this y is equals to f of x, so we are dealing with only two variables, so directly we are expressing y in terms of x, so we say that y is a function of x. Okay, now what we are going to do is we will be expressing x in respect x with respect to a third variable. Okay, so that is in terms of t. I've given you that example earlier also. Okay, so I'll take a square instead of a rectangle. It will be easier for you to understand. Okay, let I take a square with side x. Okay, and the area of this square is say denoted by y, so then we have y is equals to x square. Now in this case we had expressed y is equals to x square, which means it is an explicit function. Okay, so then you know how to differentiate it. Dy by dx is equals to 2x. Okay, so this is one example of the explicit function, right? Now in earlier exercises all the functions were in that form only, either explicit or implicit. Okay, now we know that the area, y is the area of this square whose side is x. So area of this side, it depends on the side of this square. If you increase the side, then the area will increase. If you decrease the side of the square, corresponding to that, area will also decrease, right? So y is depending on x, is it? Now when I say that the side is increasing or decreasing, right? So then the side x, it depends on a third variable, say time. Okay, so if I say that side x, okay, x increases 2 centimeter per second. Now here I'm taking a third variable. Second means it's time, which I denoted by small t. So if I say that x is increased by 2 centimeter per second, then in 1 second side is increased, right? Which means side is depending on time. If you increase time from 1 second, 2 seconds, 3 seconds, then this side will also increase. Okay, so side of the square is depending on time, and this area y, it is depending on side x, right? Y is depending on x is depending on time t, is it? Now can I say that from this, when there is a change in time, it will affect side. When side is affected, it will affect area, right? So y is depending on x, x is depending on t. So can I say that y is also depending on t? Because when you change, there is some changes on t, there will be a change in x which causes change in y. So automatically y is also depending on time t, right? So here in this case, x is depending on time, y is also depending on time. Okay, so this is one example I can take. So here I'm going to express x and y in terms of a third variable. So that is x is a function of t, which means x is depending on time t. So we write y is equals to f of x, where I take my function as f and I write it as f of x. So here I denoted my function as g, so I can write x is equals to g of t, y is equals to h of t. Let g and h be some functions, okay? So x is depending on t and y is also depending on t. So you can understand this example, right, for clarification of this concept, okay? So parametric form, when you put a function in parametric form, it means you are introducing a third variable in with respect to which you are expressing both your variable x and y, okay? So in parametric form, you will have a third variable, okay, and x and y both will be expressed in terms of this new variable t. Now this can be any variable. Here I taken t. You can take theta also as your third variable. You can take any variable you can take, but you will find that in your book most of the time variables are either in t or in theta. So this is the standard way of writing a third variable when you are expressing a function in parametric form, okay? There is no hard and fast rule that you always have to take variable t. You can use other variables also, okay? But x and y both should be expressed with respect to that third variable, whatever you are taking, okay? So in parametric function in parametric form is where we are expressing both x and y in terms of a third variable, okay? Now we will see how we will differentiate such function, okay, when x and y have been introduced, expressed with respect to a third variable t, then how we are going to find the derivative. Now you remember that even though actually what we have is our original function is y is equals to f of x. That you cannot change, okay? Throughout our syllabus, we are always taking y as the dependent variable, x as the independent variable, right? Okay, even though we had here expressed x and y in terms of t, but y is depending on x. That is there always, okay? So when you are asked to differentiate a function, whether it is an implicit function or parametric form or exponential log function, any function, okay? Whenever you are asked to find the derivative or differentiate a function, you always have to find the rate of change of y with respect to x, okay? So even though here we had expressed x and y in terms of a third variable, when you are asked to differentiate such function, you are asked to find out dy by dx, not dy by dt or dx by dt, okay? So you must be knowing this. Dy by dx means it is the rate of change of y with respect to x. Is it? You are clear with this notation? When you write dy by dx, it means you are finding the rate of change of y with respect to x. When I write dy by dt, okay, then this is equals to, what do we have? This is the rate of change of y with respect to t. Okay, you are finding the rate of change of y with respect to t. As you make some changes on t, what will be the change on y? So that we denote it by dy by dt, okay? When you write dx by dt, then it is the rate of change of x with respect to t. So here this is your, as you change, make some changes on t, what will be the rate of change of x? Okay, so that we are finding out dy by, dx by dt. Okay, so you should be clear with this concept. So any function, whether it is I'm repeating it, whether it is a parametric function or implicit or explicit or logarithmic function or exponential function, inverse trigonometric functions, whatever functions you have, when you are asked to differentiate, here I'm talking in the syllabus, right, of a textbook, in that case, always you have to find out dy by dx at the end. Okay, you are not asked to find out dy by dt or dx by dt. Okay, so when you're asked to find out the derivative, or you're asked to find you're asked to differentiate a function, then you always have to find out dy by dx. That thing you have to remember. Okay, now here our functions, in this function x and y are expressed in a third variable t. So how we can find out dy by dx? Now that's the question. Okay, now I told you this, our original function y is depending on x. In our original function, what do we have? Y is depending on x, and since this x is depending on a third variable t, so therefore y is also depending on t. So that is the basic concept of the parametric function, right? Now we have to find out dy by dx, right? So first of all, from here I can write, since this y is depending on t, right? So y is depending on t at the end. So dy by dt. Okay, so how can we find out dy by dt is, first y will depend on x. So that is dy by dx, right? Into, okay, then this x will depend on, first y will depend on x, and then x will depend on t. So that is dy by dx into dx by dt, right? Now I hope why I'm using this multiplication sign, because in class 11 you might have studied the fundamental principle of counting. Okay, so that is when you can multiply the two cases, or when you can add the two cases, so that you know. Okay, so this is fundamental principle of counting. Means if the event is happening one after the other, okay, one after the other, they are happening one after the other, then we use multiplication. Okay, if there is option or, if this happens or that happens, if two cases, if there is option, okay, so then we use addition sign over there. Now this thing you had already studied in class 11. Okay, so I won't go in much detail. So now we have this dy by dt. Okay, that's the rate of change of y with respect to t. How this happens is, first y will depend on x, so that is rate of change of y with respect to x, and after that x will depend on t, so that is dx by dt, is it? So this is the dy by dt, right? But here we are not interested in finding out dy by dt. What we have to find out is, we have to find out dy by dx. So from this equation I will express dy by dx is equals to, so you can bring this over here, dy by dt whole divided by, you can bring this here, so that will be dx by dt, is it? So this is the derivative of y with respect to x when your function is expressed in the parametric form. Okay, so what you will do now, it's quite simple. Both x and y, they are expressed in some other variable t. Okay, so separately you will find out dy by dt and dx by dt, and then you will substitute it here. So dy by dx is equals to dy by dt by dx by dt. Okay, now here I told you many times earlier also, you will be introduced to new functions, and we are asked to differentiate that new function. Okay, that is the main thing. And while you are differentiating, the way of differentiating a function, chain rule, product rule, quotient rule is there every time, right? You are just introduced to a new function, but the way of differentiating it is always same. Okay, that you have to apply chain rule, you have to apply product rule, you have to apply quotient rule. Now that thing I have repeated so many times. Okay, now we will take few examples and see how we can differentiate a parametric function. Okay, when a function is in the parametric form. So please you note down this, right, so that later you can refer to this. What I found is, many a times the student make this silly mistake. Dy by dx is dy by dt upon dx by dt. Many students, since most of the time when you write x and y, x is written first, right, y is written second. So many a time what the student do is, they find dx by dt, dy by dt, and when they substitute dx by dt, they keep it on the numerator, right? They write dx by dt upon dy by, so that gives you a incorrect answer. So you have to be careful. So dy by dx is dy by dt upon dx by dt. Okay, So this thing you will remember. Now I'm going to take a few examples. This is very simple, okay? Only this part you have to remember. So whatever you were doing in the previous exercise, the same thing we are going to do it here, but only your function will be expressed in a new way, and you have to do two differentiation, and you have to substitute here to get the derivative dy by dx. Okay, I will do these three examples to make you understand it in a more better way. Okay, first one is, now all these three question is first and second, it is differentiate. Your question will be given in the form of differentiate these two functions. So question number 1 and 2, 3 is slightly different. Okay, for question number 1, your x is 2at square and y is 8t raised to 4, right? So here you can see now x has been expressed in a third variable t, and y is also expressed as a third variable t. Okay, now to find when you are asked to differentiate, remember that you have to find out dy by dx. Okay, in this chapter, whenever you are asked to differentiate, you are asked to find out dy by dx. Okay, so that you have to remember. Now we have this dy by dx is equals to dy by dt divided by dx by dt. Okay, so we need to find out dy by dt and dx by dt. Now we know that dy by dt means it is the rate of change of y with respect to t. Dx by dt means it is the rate of change of x with respect to t. Okay, now separately you will do this. You have x is equals to 2at square. Okay, so you find out dx by dt. Okay, so now here t is our variable. So this 2a is constant, right? 2a is constant, you keep it like this. So then you differentiate t square, so which is 2t, so that is 2 to the 4at, so that is dx by dt. Okay, now what do we have? Y is equals to at raised to 4. So dy by dt, since y is expressed in terms of t, you have dy by dt is equals to, a is constant coefficient, so you keep it as it is, differentiate t raised to 4, so that is 4t cube, right? So this is equals to 4at cube. Is that clear? Now you can put it here. Dy by dx is equals to dy by dt, which is this one, that is 4at cube whole divided by dx by dt, which is here, that is 4at. Is it right? 4 get cancelled, a get cancelled, t and this powers 2. So we have dy by dx is equals to t square, right? So this is how you will find out dy by dx, and dy by dx will be in the term of third variable at the end. Okay, so this is how you will differentiate a parametric function. Okay, now it's quite simple. Okay, now we'll take the second example. It is of the same type, so you will try to do it along with me. Okay, we have x is equals to a cos theta and y is equals to b sin theta. Okay, now a and b are constant, your third variable is theta. Okay, that will be specified. So we have to find out dy by dx. Now at this time, you do know that dy by dx is dy by dt upon dx by dt. So I'm not going to write it over here. So directly I will find out dx by. Earlier, since our third variable was t, we had found dx by dt. But here our variable is theta, so therefore I will write dx by d theta. Okay, whatever in the third variable the function is being expressed with respect to that variable, you have to differentiate. Okay, this is equals to, a is constant. What is the derivative of cos? It is negative sin theta. Okay, so that is equals to negative a sin theta. You can write it like this. And dy by d theta is equals to b as it is. What is derivative of sin theta? That is cos theta. So that is b cos theta. Okay, so we have dy by dx is equals to, we have dy, sorry, this is theta. Okay, so dy by d theta upon dx by d theta. Okay, so we have this dy by d theta divided by dx by d theta. Okay, so what is dy by d theta? It is b cos theta divided by negative a sin theta. Okay, so that I can write it as minus b upon a. Cos theta upon sin theta is cot theta, so that is cot theta. So this is your dy by dx. Okay, so it's quite simple. So you have to differentiate x and y separately with respect to the third variable, whatever it is given, t, theta, or any other variable, and then you have to take the quotient of dy by d theta and dx by d theta. Okay, so which gives us dy by dx, right? In the same way you have to do. Okay, now we'll take the third example. Now this is similar, but one thing you are asked to do is, okay, here just write down, if x is equals to square root of a raised to sine inverse t, hope it is visible, and y is equals to square root of a raised to cos inverse of t. Now you can see x and y, they are being expressed in with respect to a third variable t. Okay, so which means our function is in the parametric form. If x is equals to this and y is equals to this, then you have to show that dy by dx is equals to negative y upon x. Okay, so this you will do later. First, you will find out dy by dx. So for that, what you have to do, you will separately differentiate x and y with respect to t. So that we are going to do. So third one, we have x is equals to square root of a raised to sine inverse of t, and y is equals to square root of a raised to cos inverse of t. Okay, now you have to find out first dy by dx, and then you have to check whether dy by dx is equals to negative y upon x or not. That at the end you will do. Okay, so first you separately differentiate them and try to get dy by dx. Okay, so we are going to do that, dx by dt. Now we have to apply here this chain rule. Okay, so first you look at this. This is what is it? It is a function of this square root. Okay, so that is 1 upon, what is the derivative of root x? 1 upon 2 root x, you know that. Okay, so that is 1 upon 2 root x is a raised to sine inverse of t. Okay, into, okay, now we have this derivative of a. Okay, this we have. Now you have to differentiate this. Okay, a raised to sine inverse of t, is it? Okay, or else I will first you do this on the rough part, and then I will give you one formula over here. Y is equals to, if it is a raised to x, where base is a constant term, okay, and power is x. Now you know that whenever you have a function whose power is x, okay, then how you differentiate that? Using the property of log, if you remember. So you can do this. You can write log y is equals to log of a raised to x. So that is 1 upon y dy by dx is equals to, okay, so this is equals to x into log a, is it? So instead of this, now I can write this using the property of log. Okay, so a raised to x means you will write the power before and x into log a. That is the property of log we have. So x, okay, so log a means it is constant, a is constant. So log a as it is. Okay, what is the derivative of x? It is 1. So we just get 1. After this we are differentiating both sides. So we have dy by dx is equals to y into, you take this y here, y into log a. So we have dy by dx is, what is your y? Y is a raised to x into log a, is it? So you can note this as your formula, okay, because in some questions we need this. So for example, if you have this differentiate 7 raised to x, so then directly you can write dy by dx is equals to 7 raised to x into log 7. So this you can consider it as a formula. Okay, so now let's come to this. Hope this is clear to you. Just you note down this as your formula. if you are finding, okay, you just note this like this. This is the derivation. You can just note this. Derivative of a raised to x with respect to x is a raised to x into log a, where a is the constant. Okay, so this is your one of the formula you can use. So you note down this in your formula book. Okay, now let's come to this question. Okay, first we are differentiating this whole function, that is 1 upon 2 square root of a raised to sine inverse of t. I'm applying chain rule. Now we have to differentiate this, right? A into sine inverse of t. Okay, now a into sine inverse of t means this is some function of t with which respect to which we are differentiating it. So it is in this type. Okay, so that will be a raised to sine inverse of t into log sine inverse of t. I am applying this formula. Okay, sorry, this is log a into, now we have to differentiate the power, right? That is 1 upon square root of 1 minus t square. You know what is the derivative of sine inverse of t? That is 1 upon square root of 1 minus t square. Okay, now you see if there is any term you can cancel out, or you can keep it as it is. So then it is log a, this is constant terms, so I'll bring it over here. So I have log a upon 2, that is constant, right? Now this is square root of a raised to sine inverse of t, which I can write it as a raised to sine inverse of t raised to half. I can do that. Is it? We have this square root of x is equals to x raised to 1 upon 2. So same thing I'm applying here. Earlier we had written square root of a raised to sine inverse of t. So now I had expressed in this form. So here this power is 1. Okay, so using the law of exponent, base is same, a raised to sine inverse of t, a raised to sine inverse of t, base is same, power here is 1, here is half, so you can subtract. So this is into a raised to sine inverse of t raised to, here this is 1 minus half. Okay, using the law of exponent. Okay, so this is into 1 upon square root of 1 minus t square. Up to this, is it clear? So this is your dx by dt. Okay, now this is one thing. Now you have to find out dy by dt. Now y is equals to square root of a raised to cos inverse of t. Okay, so we are finding out dy by dt, which is, okay, so now this is first as a whole it is a square root function, so that is 1 upon 2 root x. So x we have is cos inverse of t. Okay, into then a raised to this, so it is of the form d of this form. Okay, so I'm going to apply this. So here we have a raised to cos inverse of t into log a, right? This is done. Now we have to differentiate the angle into what is derivative of cos inverse of t, that is negative 1 upon square root of 1 minus t square. Is it? Okay, so now this log a, this negative, I will bring it here, so I will write negative log a upon 2. So same as here. Now square root of a raised to cos inverse of t, I can write this as raised to half. Okay, so now this becomes a raised to cos inverse of t 1 minus half. Okay, this I had already taken out into 1 upon square root of 1 minus t square. Okay, hope up to this it's clear. Now what is 1 minus half is half. Okay, so you just write here half. Similarly 1 minus half is half. Okay, so you just note down this 2. So now I had kept dx by dt and dy by dt in the simplest form. Now I have to find out dy by dx. Okay, so that is dy by dx is equals to dy by dt upon dx by dt, if you remember. So this is my dy by dt. So I will write negative log a upon 2 into, okay, so can I write a raised to cos inverse of t raised to half, I can use now root. So this is root of a raised to cos inverse of t into, okay, 1 upon square root of 1 minus t square whole divided by, okay, dx by dt, right? That is log a upon 2 into, now this term a raised to sine inverse of t raised to half, so I can use square root. So that becomes square root of a raised to sine inverse of t into 1 upon square root of 1 minus t square. Is that clear? So all the basic things I'm following here, right? Now you can cancel the terms, okay? So log a by 2, log a by 2, you can cancel this 2. 1 upon square root of 1 minus t square, 1 upon this 2 I can cancel. So I have dy by dx is equals to, from here I have negative a square root of a raised to cos inverse of t divided by square root of a raised to sine inverse of t, okay? So we have dy by dx is equals to negative. Now square root of a raised to cos inverse of t, this one, is it, are these two same? So this is equals to y. So for this I can write y divided by, and this one a square, this is equals to x. So this is equals to x, hence proved. It's very simple, okay? So only thing you have to remember is when a function is expressed or written in the form of parametric form, then which it means x and y will be expressed in a third variable, in terms of a third variable, and then to find the derivative, what you have to do is separately you will differentiate x and y with respect to that third variable, and at the end you have to find out dy by dx, which is dy by dt upon dx by dt, okay? So this is how you differentiate a parametric function. So this is a small topic, and here you were introduced to a new function, that is function in parametric form, and we had seen how we can differentiate function in parametric form, okay? And please, you always have to follow chain rule, quotient rule, product rule, okay? So this is the basic differentiation, and you will be given different new functions. So while you are differentiating new functions, these three basic things are remain there, okay? So always you have to apply these three. So I think this is enough for today. Actually, it's a small topic, okay? And for practice, you will do exercise 5.6, okay? It's a small exercise. So all the questions will be on differentiating parametric function, okay? So I think easily you can do this. So after this exercise, the differentiation of different types of function is completed. We had completed that topic, okay? Now in the next class we will see second order derivative, okay? So that is another topic, so we will be discussing that in the next class, okay? So till then you will complete all your works on differentiating different types of function, okay? So if I quickly recall, you should know how to differentiate explicit function, that is the first very simple type of function, okay? And then differentiating implicit function, differentiating inverse trigonometric functions using identities, derivative of what was that, implicit, explicit, okay, exponential and logarithmic, and then you have derivative of parametric function. So these are the few types of function we have and to find out its derivative, okay? So today I will stop here, and I'll see you in the next class. Thank you.